Okay, welcome to part 2. If the measure of angle K is 105, that would mean this thing here. If that's 105, alright, go ahead and write that in. Then the measure of angle P, P and L. We're looking for this angle here. Now, this is a quadrilateral inscribed in a circle. And one of those most forgotten rules about quadrilaterals inscribed in circles is that the opposite angles have to be supplementary. So I know that 105 plus whatever I'm looking for has to be 180. So in other words, I subtract from 180 and I figure this out, and that would be 75. And that's degrees. Oh yeah, I said do that. That's a good idea. Okay, and I'm about to erase it. Okay. Alright, for number 17. 17, if the arc from P to N is 100, and again that's degrees. I wish they put degrees in the problem here, but they don't. Then the measure of angle PLN, so that's this thing we're looking for. Measure of angle PLN is what? Now this is one of those times, yes, when it's across the circle, and it's like, you know, the alligator backed up over here, and it's eating the 100. So it is 50. The angle at the center of the circle, if I had one, the angle at the center of the circle would be 100, but across the circle, it is only 50. And the angle PNR, that's the one out here, same thing. I could connect the end point, or sorry, the points on the circle PN to any point on the circle. I can make an angle here that goes to P and N, and it would be 50 degrees. I could make an angle here, like K could go to P and N, it would be 50 degrees. I could move that point all the way to N or all the way to P, and the angle it makes with connecting P and N would still be 50 degrees. So this is the same. This angle here is like another one of these alligator angles. It's eating an arc. The arc it's eating is 100 degrees, so it's 50. Okay, and next one, I gotta get rid of all the measurements that are on there. It's nice about rewind, you'll see them come back if you do that on YouTube. Measure of angle K is 110. It was just 105 a minute ago. Okay, it's 110 now. Then what's P and L? And this is arc now, be careful. Arc P to N to L, this is the same thing, it's just a wider alligator. It is eating this huge arc from here to here. It would have to be double the angle over there, so it's 220, which in it kind of looks like 220. It looks like it's definitely bigger than 180. And the measure of P to L, that's just this much of the circle, would be the rest. That's not in P and L. I know it would have to be 360 minus that other angle, because that's all that's left. Okay, I'll pause for you to digest that for a second. And yeah, that rule about the arcs always having to add up to 360, that's something else I'm a little worried people are going to forget all the time. Okay, if the measure of arc E to F, okay, that's kind of sort of a weird one in the middle of the circle, is 120. And the measure from, the measure of arc G, looks like a 0 again. G to H, that's just this little part down here, is 90. Now these things look parallel, this ED line and this GH line, but I'm not sure that they are. Anyway, this arc is 120, this arc is 90, that's kind of hard to see. Then what's the measure of angle 1? Okay, this is one of those times when we've got the bow tie kind of thing in the middle of the circle. These angles in here are half of the average of that arc and that arc. So that's what I'm talking about here. I take, work for 19 here. I take 120 plus 90, because this intersection is inside the circle, it's going to be plus. Oh, and it actually kind of looks like a plus. I just thought of that. Look at this. There's your plus sign right there. Oh, cool. Look at that. That means plus. When it's out here, it means minus. I don't really see a minus for that situation, but oh, look, there's your plus. Okay. So when it's inside, it's plus. Divided by 2. 120 plus 90, that's 210. Divided by 2 is 105. I can think faster than I can write. Okay, 105. It's 105. Alright, then I think all this stuff kind of goes away now for for number 20. In 20, E to G is 100, and D to F, this arc, is 140. Oh, sorry, 40. I wrote that right. Then what's the angle EPG? Okay, we're looking for this angle here. This is one of those situations, make myself some more room here. This is one of those situations where if I've got this and this, I'm looking for this angle out here. This is half of the difference of that arc and this arc. Yeah, I don't really see the minus symbol showing up here as neatly as I did the plus just a second ago. can't believe I noticed that while making a video. See, Flipped Classroom has benefits. We still have little magical moments going on here. All right, so this one's 100 minus 40 divided by 2, which is going to turn out to be 30 in a second if you wait for my pen to catch up with my voice. Okay, 30 degrees. And I said degrees are a good idea. There we go. All right, if pH is a tangent, okay, well, fine, then all this stuff is out the window again. Okay, if pH is a tangent, which it looks like it is, now it looks kind of tempting to say EH is a diameter, but it doesn't tell me that. I don't know right away that this is perpendicular, so be careful about that. All I know that this would be perpendicular to a radius, but I don't know if the center's on this line, and you got to be careful. All right, the measure of arc GH is 90. This is a 90-degree arc here. And GPH is 25. Right in here is supposed to be 25. Then what's the measure of arc FH? Okay, so this is the same kind of situation as this, but it looks a little bit different. It's the same rule. It's just one of them has to be a tangent this time. So I have a tangent and an angle eating that arc with, oh, that's a great picture, isn't it? I know this is 90. I know this is 25. I know that this arc minus this arc divided by 2 is 25. So we're looking for this now. Let me write that down here. I know that, and I would say write these this way. Write them as the rule you know. Don't try to double things and do algebra in your head before you write stuff down. That's just going to cause problems. I know that when I subtract those arcs, divide by 2, I get 25, and I'm a little bit out of room. That would mean that 90 minus x, because here's the algebra you'd be doing in your head anyway. If I multiply both sides by 2, out of room again, but this isn't too bad. I could just 90 minus what equals 50. I can pretty much do that in my head. Or add x to both sides, subtract 50 on both sides. It's 90 minus 40 that turns out to be 50, so here you go. Okay, 40 degrees, and pause for reflection. I should have elevator music at this point. Wouldn't that be cool? Actually, I should have AC/DC music after the last page. Okay, that's enough of that. Great. Okay, so the rest of that page that I just got that last graphic off of, that was the rest of that page is questions from 9.7 to 9.8, which has to do with like lengths of the chords inside the circle or the parts of the secants that go outside the circle, that kind of stuff. We didn't do 9.7 or 9.8. So as you see those in the reviews or other stuff you come across, Khan Academy or whatever, realize we're not doing any of those length questions. We're just mainly focusing on angles and definitions. Okay. I think for this I may have to split these up and get myself some more room, so bear with me if I have to do that. You know what? I'll keep this page in case you want to see all the true-false answers at one place. I'll just add pages. All right, number 1, opposite angles of an inscribed quadrilateral must be congruent. That was the thing where, so here's my first time I'm going to do that. Just give me a second. Okay, that's a little better. There's a little more room there. All right, opposite angles of an inscribed quadrilateral must be congruent. Okay, so you get any old random quadrilateral here that's inscribed in a polygon, or inscribed in a circle, sorry. Opposite angles must be congruent. Well, I just drew one, and I tried to draw one semi-wacky. It doesn't look that wacky. Actually, it kind of looks like a isosceles trapezoid, but we're talking about whether or not the opposite angles are congruent. Definitely not. That one appears to be acute. That one appears to be obtuse. So this one definitely looks false, just by my sort of feeble example there. But what they're trying to get you to fall for here, it would be true if, sort of like the explain if false thing, it would be true if, and let me change color here, just to make life a little more interesting. It would be true if this said supplementary, right? Like we've talked about this enough. Again, this is what I keep calling the most forgotten rule. There's this one and there's another one about tangents people forget. But yeah, this would be true if they said supplementary, but they didn't. They said congruent, trying to get you to mess up on that. All right, if a chord in one circle is congruent to a chord in another circle, the arcs of these chords must have congruent central angles. Well, the thing is about this one, again, they're trying to get you to fall for something. We have one circle and another circle. Again, try to draw the two of the wackiest circles you can think of. And hey, ooh, here's something wacky. Try drawing circles with different radiuses, radii. And if the chord in one circle is congruent, oh wait a minute, if they mean congruent, does it have to have the same radius? Ooh, I was going to say if it had the same measure, then we could do this kind of wacky thing where I have one bigger than the other. Let me pause and look up here about congruent arcs. Does that mean they have to have the same radius? Okay, I take it back. I don't get to be that wacky. When they say congruent, okay, so this is good. We both just learned something. They mean, so I will cheat here a little bit. I have congruent circles now. When they say congruent chords, they mean chords. See, I'm so glad I'm doing this. When they say congruent chords, they mean that they're in the same chord or the circles have the same radius. So whatever the radius is of this circle, it's got to be a congruent circle, so an identical circle in size. Okay, so if I've got chords that are congruent, like say this semi-crazy one here. I can't get too crazy, but ooh, I could draw it another part of the circle. But assuming that has the same measure, again, I'm not sure if the tick mark thing is legal, but I'm going to do it. If those things are supposed to have the same measure, then the arcs of these chords must have congruent central angles. All right, central angles would be, let me change color slightly here. The central angle of the chord. Oh, you know what? Let me just get rid of this. This is not really important. Now that I've drawn those circles the same. The central angle would be, well, the angle from the center that it sort of intercepts that arc. Does that have to be congruent to that? Well, mine doesn't look like it. But if the arcs are the same, the radius is the same, there's no way around it. Yes, those are going to have to be congruent. One thing about congruent arcs is they have to have the same measure also. Not only does the circle have to have the same radius, but the degree measure of this has to be the same. So there's no way around it. You are forced to have congruent central angles there and there. Because the measure of that arc, which would be the same here, is defined to be the same as that central angle. So stuck. Congruent. A diameter that is perpendicular to a chord. Okay, so I need a circle. I need a diameter. I need it to be perpendicular to a chord. So I need to draw something that's perpendicular to this. It could be any one of these things. I'm trying to think about how wacky it could possibly be. It could be something like this. If that's perpendicular, it could be something like this. Whoa. It could be something like this. It could actually be another diameter. It could be, anything in between, some sort of like middle-sized thing. But I do know that the center of the circle, this is sort of given, has to be on the black segment because that has to be a diameter. The red one might be or might not be. A diameter that's perpendicular to a chord, so by my wacky chord here, I'm saying is one of the red things. So any one of these. A diameter that's perpendicular to a chord must bisect the chord. So does the black thing cut all of these red things exactly in half? Is that true? Turns out yes, has to be. I don't think that's a huge surprise, but if you've got a perpendicular diameter chord situation going on, then yeah, circles are inherently symmetrical that way. So I don't think that's a huge surprise to anyone. Alright, here we are, number 4. If a line bisects a chord, that line must pass through the center of a circle. So okay, here I've got a circle and I've got a chord. I'm going to go ahead and draw any line that bisects this chord. Well, any line that bisects the chord just has to be a line that goes through this midpoint. And they say any line that goes through that did not say they had to be perpendicular, and that's the thing that they're trying to get you on here. Any line that goes through there, well, it could go through like that, or it could go through like, it could be crazy. It could go through like this. It could go through, maybe closer to the center of the circle, but it does not have to go through the center of the circle. So I'm just trying to show one counterexample here because I'm trying to show that it's false. So sorry, not true. Had they said, I'll change the purple color of truth here. If a line bisects the chord, I could have said something like, is the perpendicular, if it's the perpendicular bisector, then that would force it to be true. If it's the line that's going through there and it is actually perpendicular, then you can't get around going through the center. But in general, that's false if all it has to do is bisect. All right. If let's get back to making another circle. If the ray GM intersects a circle in just one point. Okay, so let's draw a ray GM that goes through the circle one point. So something like that. Okay. Now it does not tell me where G and M have to go. G and M could kind of go anywhere. Let's try to make this wacky. Let's try to make it so that that the segment GM would not be tangent to the circle. Well, I don't know where G and M are on this thing. GM is just a sort of a limited kind of part of this ray. It could be right there. GM. Oh wait, I should make it so GM is a ray that goes that way. Let's reverse those. Let's call this one M and this one G. Sure. Then you think about ray GM. Ray GM starts here, goes that way. It intersects the circle in just one point, but GM is not tangent. Another way to do that, I could say that here's ray GM. Starts here and goes boom, goes that way. Then here's ray GM. It intersects that circle in one point, but that's clearly not tangent. That's not what the definition of tangent is. So again, I'm sorry, but you are false. I'm trying to think of how to make that true.